Welcome. This is 48C video 1, and we're on the second part of the chapter on motion in one dimension. Last time it was part 1, this time it's part 2. And now we're going to apply what we've learned. We're going to extend it a little bit and then apply it to real world problems. So we have a discussion of constant acceleration graphs. We began looking at graphs last time, but now we focus in on constant acceleration. We have kinematic equations for graphs. We have kinematic equations from calculus. And then we have one dimension constant acceleration problems. And then we have really what is the crown jewel, which is the one-dimensional freefall problems, which are a subset of the constant acceleration problems. So let's begin. So before we showed a series of position versus time, velocity versus time, acceleration versus time graphs that were not from the same journey. They were just either generic linear equations, or they were combinations of linear sections to form an overall complicated journey. Now let's look at a journey which is constant acceleration. So the first thing we look at is a acceleration versus time graph, and we see that it's a straight line. It could be above the origin, meaning positive acceleration. It could be below the origin, meaning negative acceleration. Either one's allowed, but it's going to be a horizontal straight line. If we have a constant acceleration, that means that our velocity changes by the same amount each second. And for a positive acceleration, your velocity steps upwards, and for a negative acceleration, your velocity steps downwards. Well, this is a positive acceleration, so let's say we didn't start at zero velocity. When our clock started, we didn't happen to be at zero velocity. That's allowed. But we started and we had the first step, and then we had the second step, and we had the third step, and we had the fourth step. And can you see how in each time interval, each say second, if you like, we've changed our velocity by the same amount. So inevitably, we get a straight line graph. Now this straight line, if we had a big acceleration, could be a steep slope. If we had very little acceleration, could be a very shallow slope. If we had no acceleration, it would be horizontal. 0 is a number, so if we had a negative number for acceleration, it would be a negative slope, and so on. So there's a variety, but each one of these graphs must have a straight line trace because it's a constant acceleration. Okay, and then let's have a look, and let's go back here and let's say, well, now let's look at our coordinate or a position versus time graph. And what we recognize, of course, is that the displacement is the area under the curve. And if I compare two displacements, one from one time interval and the second from another equal time interval, can you see how the displacement of this first section is less than the displacement of the second section, which will be less than the displacement of the third section, because the areas under the curve are getting bigger and bigger and bigger. So that means that my step in position gets bigger and bigger and bigger, my displacement. So I have a little step, and then a big step, and then a bigger step, and then a bigger step, and then a bigger step. So for equal steps in time, I get increasing steps in displacement. So can you see how with practice you can see a pattern of graphs, and you can tell if they go together because they are constant acceleration graphs? That's a skill I'd like you to have, and in fact let's do a bit of a practice on this. So in this exercise we want to figure out which of these are consistent with constant acceleration graphs. And the first one, well, the first one has a sloping graph. Let's remind ourselves to look at our axes of acceleration versus time. And this is a sloping graph. And so that's not going to be constant acceleration. It cannot be, because the acceleration by definition is not constant. This second graph, well, this is velocity versus time. And what we see here is we get something that looks a bit like an inverse velocity in time. Let's have a look. Constant acceleration means a steadily changing, a linearly changing velocity versus time graph. And this is certainly not linearly changing. So that is inconsistent with constant acceleration. This third one is a displacement versus time graph. And can you see how as time passes you take bigger and bigger and bigger and bigger steps in displacement? Constant acceleration means steadily increasing velocity, means increasing displacement steps in time. So that is consistent. That could be. Let's have a look at this. D. That's an acceleration versus time. Nice, steady acceleration. Yes, that also could be a constant acceleration graph. A steadily changing velocity, a linear velocity graph, but it's negative. Does that matter? Oh, I'm adding on an equal change of velocity per second, but it's a negative change in velocity. Oh, that's a negative acceleration. It's constant acceleration. It just happens to have a negative value. That's consistent. Then the final one, displacement versus time. And again, I have a increasing displacement with increasing time, with steadily stepping time intervals. So I have, yes, that is also consistent. Make sure that you're comfortable with doing this skill. Make sure you're comfortable with it. Now, my personal feeling about graphs is that they're really, 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 really valuable. So, in this next slide, we see some mathematical algebraic equation derivations done from graphs. So we can actually use graphs to develop equations, just as we can use equations to develop graphs. So I've set up here several graphs. Let's remind ourselves this is a velocity versus time graph. In each case, these are all the same graph. I'm just going to analyze the same graph in different ways. And in each case, it's a linear increasing velocity. So we'd say a positive acceleration, which is constant. And what I'm doing is I'm trying to analyze this graph in different ways. So the first thing to recognize is a straight line graph. So I can say, well, for a straight line graph, y is equal to mx plus b. And we can just do some translation. In this case, y is the answer I get after a certain time, which is vf. So there's my vf value. And then my slope is my acceleration. So my slope is my acceleration. I'd actually put down delta t. I prefer delta t. It's not recognizing the delta. I prefer delta t, meaning it's a time interval, delta t. So delta t. B is the y-axis intercept, which is there. So that's B. So what I can say is the take-home equation, which we tend to remember, we have to remember, is Vf equals Vi plus A delta t. In this second interpretation, I say, well, you know, this is a velocity time graph, so the area under the velocity time graph will equal displacement, and it's a trapezoid, so the area mathematically is equal to the average of the two sides, so it would be the HL, which would be the H on the left hand side, and HR divided by 2 to get the average, and then multiplied by the width. If you think about it, what you're doing is you're cutting off this little bit of triangle here and you're slipping it down there, and you're saying, look, it's a triangle, it's a rectangle. Let's clean this up a bit so that because I want to now explain the physics. So what we have is we have our delta x, again it's missing out the delta, our delta x is equal to 1/2 Vf plus Vi. This is my Vi, my initial, and this is my final. I'm going to add those together and divide by 2 to get the average, and then multiply by the width, and the width in this case is delta t. So I can write this down as x is equal to 1/2 Vf plus Vi, or Vi plus Vf, it doesn't matter, delta t. Second equation to be remembered. Third equation, well, is a velocity versus time graph. And again, we're going to recognize that the area under the graph is equal to the displacement. But now I'm going to recognize this as being a combination of a triangle and a rectangle. And I'm going to say, well, for the triangle, for the rectangle, it's the base times the height. And for the triangle, it's 1/2 the base times the height. It's the same base, of course, but it's a different height. Okay, so we have our basic equation. Let's clean this up so we can actually express it in terms of the kinematics that we're interested in. And what we can see is that, okay, well, delta x, the displacement, is equal to Vi times, this is my Vi, times, from there to there, Vi times delta t, from there to there. So there's my rectangle on the bottom. And then I have my triangle, which is 1/2, and the height is Vf minus Vi. It's the difference between the two of them, so that's Vf minus Vi times the base, which is delta t. You see where that comes from? Now that is a valid equation, but for various strategic reasons it's useful to rearrange this equation, to try and convert it slightly. So I'm going to go back over here to the first equation I did, and I'm going to recognize that Vf minus Vi is equal to A delta t. And then I bring that over here and I say, well, delta x is equal to Vi delta t. That stays the same. But this 1/2 A t squared, this next section, the Vf minus Vi equals A delta t, so that's going to be A delta t, and so I have times A delta t squared. So we have a delta t in there, it's squared, and this is a delta t. In this last column, I do a derivation. I say, well, mathematically Vf equals Vi plus A delta t, and Vf squared is equal to Vi plus A delta t squared. Vf squared equals Vi squared plus 2 Vi A delta t plus A delta t squared, just multiplying out. So Vf squared equals Vi squared plus 2A Vi delta t plus 1/2 A delta t squared, which gives us Vf squared equals Vi squared plus 2A. It turns out it's delta x. So down here I can say Vf squared equals Vi squared plus 2A delta x. We have 4 equations of kinematics, and I want to point something out to you. If you think about it in terms of parameters, well, we have Vi, we have Vf, we have A, we have delta t, and we have delta x. Initial velocity, final velocity, acceleration, duration, and displacement. 5 parameters. And if you look at this one, it's got 4 parameters in the equation, and the parameter we're missing is delta x. And in this equation, we have 4 parameters, and the one we're missing is A. And in this one, we have 4 parameters. That should be a delta x. We have 4 parameters, and the one we're missing here is VF. And in this one, we have 4 parameters, and the parameter we're missing is delta t. With those 4 equations, we can cover pretty well every kinematics situation we want to look at. We can do the same thing using calculus. Just look in the book for that. Let's do some examples. At time t equals 2 seconds, a sports car is at rest. So let's just draw it as our sports car. The clock, t equals 2 seconds, and VI is equal to 0 meters per second. At t equals 6 seconds, so t equals 6 seconds, sports car has a velocity of minus 12, so V final is equal to minus 12 meters per second. Let's put arrows on these things just to reinforce the direction that it's going in. This one's not going in any direction. I'm just going to put it forwards, but it's not really going in any direction because it's at rest. Then it says, what is the constant acceleration for this journey? I'm a big believer, especially when you first begin, of drawing a diagram, because you're going from words to pictures, and then you make a list of what you know and what you don't know. And what I know is that VI is equal to 0 meters per second. I know that VF is equal to minus 12 meters per second. I know that T initial is equal to 2 seconds. I know that T final is equal to 6 seconds. And I'd like to know what my acceleration is. Now notice T initial and T final. Time interval or duration equals T final minus T initial, which equals, in this case, it equals 6 minus 2, which equals 4 seconds. So what I've got is I've got a VI, I got a VF, I got a delta T, and I want an A. And that jogs your memory so that I can say, oh, I know what to do. I'm going to say VF is equal to VI plus A delta T. And I prefer to substitute numbers in to the original equation because sometimes you find there's happy coincidences where things have zeros in and they just go away. So I say, okay, well, let's VF is going to be minus 12. Put it in parentheses because it's a thing. And then VI is 0. And then A is what I want. And delta T is 4. So I'm going to say A is equal to minus 12 over 4, which equals minus 3 meters per second squared. And there's my answer. Let's do another one. At t equals 3 seconds, a red truck has a velocity of 6 meters per second. So we have t is equal to 3 seconds, and my truck has a velocity of, let's have a look, VI is equal to 6 meters per second. Red truck has a constant acceleration of minus 4. Let's draw that in. A is equal to minus 4 meters per second squared throughout the journey. We couldn't use these equations if the acceleration was not constant throughout the journey. That's really important. And then what is the displacement of the red truck after 8 seconds? Okay, so we're traveling in this direction. We've got a negative acceleration, so we're slowing down, but I'm going to do my displacement in that direction because that's the direction we're heading in the beginning. I'm going to say here's the truck at the end. My time is equal to 8 seconds, and I want to know displacement. Again, I have to visualize. I no longer look at the words. Once I've got the diagram, I don't look at the words. Let's make my list. I go VI is equal to 6 plus 6 meters per second. I say that A is equal to minus 4 meters per second squared. My delta t is equal to my final time minus my initial time, which is equal to 8 minus 3. There's no law that says I have to start the calculation when the clock says 0. And that equals 5 seconds. And then what am I looking for? I'm looking for my displacement. So again, I have a VI, I have an A, I have a delta t, I have a delta x. And it jogs my memory, and I say delta x is equal to VI delta t plus 1/2 A delta t squared. So I say delta x, which is what I want, is equal to VI plus 6 times delta t, which is 5, plus 1/2 times A, which is minus 4, times delta t, which is 5 squared. So delta x is equal to plus 30 added to 5 5s are 25, 4 25s is 100, a half of 100 is 50, and it's negative 50. Ooh, so that means that my delta x is actually minus 20 meters. Let's think about that. So what happened was I started off with a positive velocity and a negative acceleration. And so my object was slowing down, slowing down, slowing down as time passed. At some point it stopped, and then I had a negative velocity and a negative acceleration. So it speeded up, speeded up, speeded up, speeded up, speeded up, and then I stopped the clock. So can you see how, because I waited long enough in my time, my delta x was negative? Let's do another one. A red truck has a velocity of plus 15 meters per second. So VI equals plus 15 meters per second when it crosses the starting line. There's my start. It has a constant acceleration. A is equal to minus 3 meters per second squared. So we know that if the velocity is positive and the acceleration is negative, it's slowing down. What is the velocity of the red truck when it passes, when it has a displacement of plus 5 meters? So here's my displacement, which equals plus 5 meters. And I want to know what the velocity is, V final. So I make a list and I say VI is equal to plus 15 meters per second, and A, of course, is equal to minus 3 meters per second squared. I know that my displacement, delta x, is equal to plus 5 meters, and I'd like to know what VF is. Cool. Jogs my memory. VF squared is equal to VI squared plus 2A delta x. Notice I went from words to a picture, I went from pictures to a list, I went from a list to an equation, and now I'm doing sums. So VF squared is what I want, is equal to VI squared plus 15 squared plus 2 times minus 3 times plus 5. So VF squared is equal to, that's going to be 150 plus 75 is going to be 225. 225 plus 5 3s are 15, 2 15s are 30, minus 30, which equals 195. That's a positive. So VF is equal to the square root of 195. And that equals, I get my calculator, and I go second square root 195, enter, and I get plus or minus 13.96 meters per second. And that can be rounded to 14 meters per second. Now, in my 9 times out of 10 you're going to get this as a open-ended question, so there's no answers, but occasionally you might see it as a multiple choice, and you'll see that I have plus 14, plus 16, plus 195, and plus 225. So no negatives on here, but actually let me point something out to you. I am moving to the right and slowing down, and so my journey goes like that. So at this point, when I cross the displacement, I have a positive VF, and at this point I have a negative VF. And so in truth the answer should be plus or minus 13.96 meters per second. And both answers in this case are valid. It doesn't say what is the velocity of the red truck when it passes the displacement of plus 5 meters for the first time. It just says plus 5 meters. There are some times when it's obvious whether you need the positive route or the negative route, and that's what I'm checking as an examiner to find out, did you pick the right one? Because if you pick the wrong one on the second part of the calculation, you may end up with an incorrect answer. Let's do one more question. Blue truck has a velocity of plus 15 meters per second when it crosses the starting line. So we have a truck VI equals plus 15 meters per second, and it's crossing the starting line. It has a velocity of plus 5 meters per second when it crosses the finishing line. It travels with a constant acceleration, but it doesn't tell you what it is, and it takes 8 seconds from traveling from the starting line to the finishing line. And then what is the displacement of the finishing line? Interesting. It has to be a constant acceleration, even though we don't use it. It has to be a constant acceleration. So we have a truck starts at plus 15 meters per second. When it crosses the finishing line, it has a velocity of only plus 5 meters per second. We know it's a constant acceleration, so we can apply the kinematic equations. We have a time interval of 8 seconds, and I want to know the displacement. Let's make a list. VI is equal to plus 15 meters per second. VF is equal to plus 5 meters per second. Delta X is what I want, and delta T is 8 seconds. Okay, sorry, delta X equals 1/2 VF plus VI delta T. Cool. So delta X is what I want, is equal to 1/2 VF, that's plus 5 plus 15 delta T times 8. So delta X is equal to 1/2, that's going to be 20 times 8, that's going to be 80 meters, positive 80 meters. And there I have it, positive 80 meters. So there's 4 examples. We used each one of the kinematic equations once. Some of them are used more often than others. Delta x equals VIT plus a half AT squared tends to be used a lot. VF equals VI plus AT tends to be used a lot, just because of the way that the problems tend to be phrased. Notice in each case I'm using the same approach. I am reading the words. I am drawing a diagram to form a picture that replaces the words. I extract a list from the picture. I use that list to define my equation. I then do math. The math in some ways is what? The final step in a physics process. So make sure, if you tend to do this by just writing down numbers, be careful, because you're missing a lot of steps, or you're doing a lot of steps in your head, and that means you cannot check them at the end of a test. So it's good to write things down. It's good to use the paper as a layout scheme. You know, I believe that somebody looking at my work could follow what I did. If I just had numbers on a page, I don't believe they could. I can check my work very easily because I wrote enough of it down. So learn the approach, don't try to remember these questions. Notice that there's a similar approach in each case. And practice, practice, practice. There we have it.